Okay, so first things first. Oh, I'll then start sharing my screen. And then Mark, since I don't think I've had you in one of my, what's it called? One of my study groups before, I'm just sharing this with you. This is where the notebooks, some of the notebooks I'm gonna be going over today. So I'm just sharing this through the chat. But we'll specifically be looking at like mod 4, and then we'll talk about recommendation systems and afterwards PySpark. So just kind of know that's there. And then I'll make sure to send you the recording too, but it should be online. Anyway, administration stuff, don't worry. So first thing we're going to talk about is recommendation systems. So first of all, like what is a recommendation system? Well, hopefully like, kind of look at the material for the curriculum. It's relatively clear. It's like, basically it's like if you want to recommend something based on a user and like basically what a user likes. And this is kind of an interesting idea too, because I mean, I don't know if you guys are familiar with like how essentially most of like, let's say like things like Blockbuster, which pretty much doesn't exist anymore, but like those video movie stores and stuff like that, or rentals. One thing they would do you know how they decided what movies to put into their shelves? Do you guys have any idea?
What's a recommendation system modeling?
Nope, not at all. Pretty much not. They basically just pick the most popular movies and that they would feel that people generally would have. So this is something was interesting is when Netflix came out before they even did streaming, which is kind of weird when you think about it. But Netflix, didn't do streaming. They basically were a mail-in system for Blockbuster. So they would mail you, your DVDs, right, to do this. And they were able to do this because it was super cheap to mail a DVD versus like a cassette tape, or not a cassette, a VHS tape. So kind of blast from the past. But this is one of the reasons why Netflix did really well is that Blockbuster essentially would send just the most popular movies, which makes sense. Like, okay, like we can only put so many movies in our shelves. So we have to essentially give like what's going to be the most popular, like if we're going to have only 50 or room for 50 different movies, we want to make sure those movies are going to be popular for most people. And so Netflix actually did the interesting thing, or at least maybe not on purpose, but they had more obscure movies and TV shows and things that you could rent out that most people couldn't get in any other Blockbuster or any other movies kind of store. And this is what the idea of long tail is. So this long tail right here, basically, this is a distribution. This is directly from Wikipedia, but basically it's a distribution where most people, well, you see this light green, hopefully, and this yellow, that might be hard to see, but this light green about from here to the left represents about 50% of the population. And basically you can see like, these are like, you can imagine how many people enjoy this movie on the x-axis. So x-axis essentially like each movie. And essentially there's like a few movies that everybody like really likes, like a lot of people like, and then it gets like more obscure movies. Like, well, some people like this movie, some people don't kind of deal. And then you get these really obscure movies. So like only like 3 people like really like this movie kind of deal. And so Blockbuster were basically, and other movies, rental stores were focused on this part of the graph. And Netflix actually did really well with this part of the graph over here, basically really obscure movies that basically they couldn't get anywhere else. So basically the reason why they were able to do that is because they had more choices. They could just mail you any movie they want. So this actually comes in the idea of big data. The only reason why recommendation systems can really work is if you have essentially a large amount of data. We'll talk about this like in a second, which is technically second 38, but like when you have big data, you have a large volume, a large variety, large velocity, right? Basically, you can give out a lot of information very quickly, or you have a lot of information. So this is where recommendation systems really work well. So what you're trying to do instead of predict is like, oh, well, let's just get the masses, whatever everyone likes, we'll just do that one. You say, well, let's look at this specific person and try our best to, predict off there. So the thing is like, I kind of make a little joke here. It's like, oh, it only knows some information we can use to predict, right? Like obviously, well, we're data scientists, right? So we can actually use data to figure out this stuff. And that's actually really cool is that the reason why we're able to do this is really because of large amounts of data. Basically, we have a large amount of what people like, what people don't like, and we can figure those things out versus trying to figure out what obscure movie you have. Like if you think about doing this yourself, like you can't like reasonably actually find what movie that's really obscure, that you'll like. And this is where recommendation systems can basically come into play. So kind of going forward is that there's one, well, no, I don't know why that's broken. I was doing that earlier, but okay. Basically, it's like, how would you, like, if I was to say, like, just to come to you, not as a data scientist, it's like, you know, how would you figure out what movie to recommend? So like, you'd say, hey, I have a so-and-so friend. What movies would you recommend to them? What are things that you could do? So the simplest one that's already here. A dumb way, a dumb way is like, well, lots of people like it, so you must like it too, right? So like really popular movies, like where maybe it's like, yeah, a lot of people like this, but maybe they're a little more subtle tastes, right? Maybe they're a different special snowflake that they have their own, you know, taste and everything like that. But if you go besides that, what other ways might you do to actually recommend a movie to someone? Like just think in the real world, like if someone asked like, hey, like what movie should I watch? Like, will you just, I mean, one option really is just say, oh, this movie's really popular, or like, oh, I really like this movie, you should watch this movie. But kind of going deeper into that, there's other ways we can do it. Like, you know, we can learn about the person, right? We can learn about the person, about what they like and stuff. And that's essentially what we do with big data, right? So this hopefully goes pretty obvious. But I kind of mentioned the dumb way, which is like, say, oh, lots of people like it, so you'd like it too. That's kind of like when we do like a linear regression line. If you remember back when we did linear regression lines, when you essentially do I say like the dumb way of modeling basically is like you take the average and then you compare it with your model. That ends up being your R squared value, basically comparing it with the average. You say everything's just the average. That's essentially what these are. Like, so there's nothing, like there's a lot of people who are just like, you know, will be okay with these movies, but maybe it's not like the best movie because it's isn't that specific person. Because we're not all sheeple, right? We're like, we all like different things and everything like that. So the smart way to do this is actually, I don't know why my little things are, you see that's broken. Here. All right, but the first way, and this is where the curriculum talks about, is content-based. And so the idea here is like, if you like Iron Man, you like other Avengers movies, which makes sense. Like if you liked Harry Potter, you might also like things that are maybe along those lines too. Maybe you can say, oh, if you like Harry Potter, you'll like other Harry Potter movies, but like, oh, maybe you'll like Lord of the Rings. But even then, that's not as simple. Maybe it's like, well, if you like Harry Potter, maybe you're in that age group, you know, like that happens to like kind of like that teenage, you know, kind of dramas and stuff. So for example, things like people like The Hunger Games versus, I don't know, something similar, like Divergent or Maze Runner. Like those are kind of like similar, even though they're not the same exact thing, they have that same feeling to it. Or it's the same idea as like if someone likes a kid's movie, someone else will like a kid's movie too. So this is like content based, which is, you know, not a bad way to go, right? Like similar if you like one movie, you probably will like other similar movies, okay? The next part is more collaborative filtering. So collaborative filtering, you can think of like collaboration, like you have multiple people basically saying like what they like. And so the way I kind of imagine this is like, oh, like if I met someone like, oh, you're just like my brother. Like he really likes the Lego movie. Like, you know, it's like people like the Lego movies like that. Isn't that a kid's movie? And they're like, no. Like I think like your personality wise, like you'll enjoy this because it's kind of witty and everything like that. It doesn't feel like a kid's movie where you can find things that you wouldn't necessarily have associated yourself with. So this was really interesting is that this tends to be like, in my opinion, the more powerful and more interesting way of recommendation system. And this is where we have certain things like, what's it called? We have like recommendation systems like even from Google and stuff like that, or from like Netflix, where you're like, whoa, like I would have never picked this, you know, movie or this, you know, suggestion, but other people who have similar taste to you have picked that for you. So essentially they're able to pick things out. So that's what collaborative filtering is. And these are the two based ways that I think the curriculum really talks about. And these are kind of like more of the state of art stuff, is that you either base it on content or collaborative filtering, which in these terms, so you read this, if you like Iron Man, you know, you like other Avengers movies, and like, you know, if you're like this person, you'll probably like this movie. Those are very simple to say, but then you can think about this, like, well, what makes like other movies like Iron Man and like other movies, like let's say other superhero movies, like Iron Man and Spider-Man, like we as humans probably intuitively understand that, but like how do you make sure to describe that to a computer, right? That's not a simple, easy thing to like describe and quantify. And so we'll talk about ways to do this. And same thing with having similar basic collaborative filtering, where you have someone who is, you know, likes these certain things, But how do you make sure that those two people are actually alike? Like, what does that mean exactly? And this is where we can actually talk about, like, okay, now we can quantify this part. So this leads us into our first option, which is neighbor-based or memory-based collaborative filtering. Oh wait, actually, I don't want to show that one first. Sorry, I want to talk about, oh no, I'm sorry. That is it. This should, oh, hey, collaborative filtering, that's fine. This also works for content. Sorry, I had something else in my mind. But basically neighbor-based or memory-based collaborative filtering basically says who are similar to each other. This can also be content filtering. That's what kind of threw me off, or content-based filtering. So you basically, what you have here is you say things that are alike, will be close together in higher dimensional space. So if you can kind of essentially, if you could somehow filter, like list out all the properties of this movie, you know, in that dimensional space, you would have something that's very similar to each other. So usually what we'll do here is like a K nearest neighbors, right? K and N, and see how close something is to each other. And again, this comes back to like clustering. Is the concept is that things that are quote unquote close together must be similar to each other. And so what kind of comes down to is like, okay, once you have that, it's not necessarily a difficult thing to like once you start with that concept, it's not that difficult to like say, okay, we can go ahead and proceed forward. The biggest part is basically the similarity metrics and basically deciding what is close, right? Because close can be a lot of different things. So just know, for example, like the curriculum talks about Pearson's correlation, which is like the lowercase r that we've seen before, goes from -1 to +1. So that kind of basically saying like, oh, is there a positive correlation or a negative correlation? And I think I mentioned this before, way before, but I always say like your exact opposite is like your best friend, like in a movie recommendation. Like if you know someone who is really like hates every movie that you like, but loves every movie you hate, they're like the perfect recommendation system because you just ask them, well, what movie do you hate? And they're like, oh, I hate this movie. And then you'll know you like it. So like a negative correlation is a good correlation essentially. But again, Pearson correlation, that's how you get a similarity, or that's one option. Cosine similarity, this is much like we haven't talked too much. We kind of hinted a few times, like, oh, cosine similarity. Way you can kind of think about this is like basically how similar vectors are. And the reason why this is important is that we'll tend to do something called embeddings, which we'll talk about in a second. But when we do embeddings, basically we create vectors, feature vectors out of whatever we're trying to look at, whether it's like, let's say users in movies, right? And say like, how similar are these vectors together? And so that's what this cosine similarity, basically it's measuring that distance between the two. And what's nice is that you can do this with multiple dimensions. It doesn't have to be, you know, in my mind, I always think like cosine is like 2-dimensional, but you can actually use this with the vector that is in n-dimensional space. And it goes from -1 to 1. Jacquard similarity, I was trying the best way to like kind of get a good summary for Jacquard similarity, but basically like you can think of it, it's like, did they even rate this? Like, and the concept on this might seem kind of weird. Like, why does it, like, why would we only count if they rated like a movie or something like that? And you can kind of think of it like everyone's like, you know, 1 to 5 stars. Like there isn't really a big base of like, what is a 5-star versus a 2-star versus a 3-star? Like everyone's 3 stars are different from where they, you know, place that. So Jacquard similarity could be something along the lines where you aren't necessarily looking at like the degree of how much they like something. This would be equivalent to like thumbs up and thumbs down. And this actually is something that's really interesting is that if you watch Netflix and you pay attention to the recommendation systems, they used to have stars or something along those lines. But now they have just a thumbs up and thumbs down. And that's because of that reason. It's like, well, basically you can say you like it or you don't like it. Versus a star system where star systems, you know, some people say, oh, 2 stars means like, you know, like, it's like, well, I kind of liked it. And other people are like, oh, like this is an awful movie. I don't want to watch this again. And some people say, well, it's like, it was all right movie, but they put 4 stars. So this is where like these star variations really like differ from each other. Interesting enough is that once they have enough information about like how much people just, I mean, essentially what happens, the thumbs up and thumbs down are almost in a sense like extra boosters because that's not what they base it off of. They both mostly base it off of, did you watch the movie or not? You know, if you watched all the way through the movie, you probably like that movie, at least in some way. So that's kind of like where the recommendation system comes through. And the thumbs up and thumbs down is basically like an after thought, because most people won't do that. And usually people have either very specific demographics, people who really care about rating movies, or they're people who like really like this movie or really, really hated this movie. And they want to make sure like Netflix knows. So those are kind of different parts. And that's why, interesting enough, like having a single metric usually isn't enough because everyone's a little different. But anyway, these are the different similarities. There are a few things, other ones you could possibly use. Like you could probably find some obscure one. Cosine similarity is probably the most common for recommendation system that I've seen, which kind of makes sense because we'll do something called embeddings with vectors, and you want to basically see how closely related a vector is, right? So this is neighbor-based. The curriculum kind of walks through a little bit. Basically, you can think of it like doing k-nearest neighbors and just figuring out what things are close together, what are they clustered together, and then going from there. So any like conceptual questions about this concept or the recommendation systems in general? Okay, thumbs up then, thumbs down, sideways. Cool. All right. Awesome. So that leads us to matrix factorization, which I just like, I love. I think it's so cool that you could actually do this. So the first thing you have to do, really to do like this thing called matrix factorization, which we'll talk about, is getting something called embeddings, which I kind of alluded to. And embeddings get, I don't know how I put it like this, it should be like embeddings, getting latent properties. So we could do something called embeddings. And basically embeddings are creating like a vector that will inherently like incorporate latent properties that best predict like the system. And that kind of seems very like vague, like kind of feeling. But basically the idea here is that what we're going to do is we're going to take like things like discrete elements, like, oh, they rated this movie, they rated this movie of a number or so on, right? And give it like 2.3 stars or 2.5 stars. And they take something more discrete, we're mapping it over to a vector space to say specifically, how do those stars map over to that specific user? And so I'll kind of show this idea here. But the idea of this latent properties is probably the most powerful thing. It's kind of similar to like what we did with PCA. If you remember, basically saying like, okay, like we have these features, like, I just went through this a while ago, so I'm trying to like, remember what I had done. But like, if you imagine like your latent feature, or not your latent feature, PCA, your principal components, you have your main features, like let's say for a house, you have like things like, oh, the windows, how many windows there are, how many doors are there, how many rooms there are, what's the square feet. But your like principal component could be something like, what is, the size of the house, or what's the feel of the size of the house, which is independent on square footage. Maybe if you have a lot of windows, the house feels bigger. How many rooms can also factor into how big the house actually feels. Like if you have many, many rooms, but like in a relatively small space, it'll feel smaller probably versus having the same space, but fewer rooms. It might feel more open and all that stuff. So that's what PCA does. This is kind of like the idea with embeddings. It's like you're kind of capturing this, like I call them like super features, but basically something that's describing this that's not directly told in here. So the intuition here is if we go back to a movie scenario, right, is that you essentially have your movies and you have your user vectors, right, your embeddings. And so let's say you have like a movie vector like the Minions, right? That shouldn't be Minions. But if you have something like the, just call this me. If I don't change it now, I'll show it later. Okay. A movie's vector like Minions, right? And so basically you can do this embeddings. Let's say, okay, it's a 0.3 here, 0.4 in this dimension, and negative 0.8. And so those things can kind of like, you can think of it this way. It's not actually how it does, but like you can think of it, is that this 0.3 represents, how funny it is, and 0.4 can represent like how romantic it is, and maybe negative 0.8 can represent something like how much action is there, is it an action-packed movie or something like that. And you can think of like, you can have many dimensions on this, not just 3. So the idea here, again, is that you essentially are representing this movie Minions in a vector by basically creating these latent features of like thinking, oh, how is it a comedy? How funny is the movie? How romantic is it? How much action packed is it? So you can kind of see, like, you can probably think like in movies in your head right now. Like if you think of like romantic comedies, you'd probably have a high, comedy threat, like dimension, and then like a high romance dimension. Of course, in reality, the when you create these embeddings, you won't actually know, like what's it called? The system is gonna, like your algorithm basically is gonna find latent features that you probably wouldn't have discovered. Kind of like with principal component analysis, that concept's there for like, we know like this super feature, but in reality, it's probably not something like a human would have guessed or created by itself if it have to like understand, given like the understanding of a person, right? But the concept's there. And then something similar happens with a user vector, where you have the same number of like dimensions, right? And essentially what we do here is like, okay, we can take these parts, say like, how much do they like comedy movies? How much do they like romance movies? How much do they like action-packed movies? And that's kind of like their user preference kind of deal. And so with that, you can basically take those two parts, and we essentially can just do a dot product together and say, okay, here's the features of the movies, like this embeddings of the movies, embeddings for the user. We can do a dot product, which basically will just multiply these two numbers, let's say like 0.3 and 0.7, 0.4 and minus 0.1 and negative 0.8 and 0.8, and combine them together, basically add them all up, sum them up, and you would have a single number that can represent, you know, for example, the number of stars they would have, or what they would do, or like, you know, how much they would prefer this thing. And basically it's just seeing how well they match. So it's kind of cool, like be able to actually use this like concept here. And so I'm going to point to this guy right here. Is I highly recommend, and I'll send it in chat right now since you guys are here, but I highly recommend this learn lesson. I'm not learn lesson, Kaggle, like they call it Kaggle Learn, but basically like a Kaggle like learning lesson. And to be honest, a lot of times Kaggle's lessons can be a hit or miss. Sometimes I feel like, oh, these are really great. Other times I'm like, it seems to be lacking. This one I felt has been really good. This guy, Colin Morris, is pretty good at like writing this stuff, but basically goes through much closer to like an actual, what's it called? A recommendation system of movies, kind of what I described. And he talks about, you know, what embedding layers are, like how to do embedding layers, doing matrix factorization, which is like the main meat here. So just know that, what's it called? Like I would say like this is kind of like the description from Learn. In Learn, they talk about, you know, doing, what's it called? Matrix factorization. This one I feel does a really good job of like intuitively explaining, like, here's an example of movie ratings. And you can see like how similar movies have similar vectors. So for example, I'll just show you, I think here's a visualization of this. So like he basically has a bunch of movies with a bunch of ratings, right? And he has it combined together. And so here's all the different movies. And so you can see like, he flattened this down with TS&E. Basically it's kind of like dimension reduction, right? Or dimensionality reduction. And so essentially right here, you can see like the different movies, and you can see there's a little bit of a clustering here, some clustering over here. And so he starts picking out specific movies. For example, he picks out like Harry Potter. Like, okay, Harry Potter, and you can see anything with Harry Potter is grouped right here in the screen. And so if you zoom in a little bit, you can see Harry Potter and the Sorcerer's Stones, all of them are very similar to each other. They're very grouped close together. But you notice here, really close to Harry Potter, I don't know if you guys can read this too well, but it says the Hunger Games, those part series, stuff like that, which might make a lot of sense when you think about it. And he kind of talks about this, like why this is probably true. It's like, well, Harry Potter is like a series of movies, right? Like it's not just a one-off movie. It's like meant to be a full story structure. Same thing with the Hunger Games. Also, they feature kind of like teenage characters and like different environments. And so you might see like, okay, there might be like a similarity in that sense that like, I feel like if I said like the Hunger Games and Harry Potter, and like are those relatively similar? You probably be like, yeah, I can see how they're similar, but you probably couldn't describe it in words, right? Exactly why it is. Like maybe you could kind of, depending like your familiarity with it, but you could probably get just a general feel. It's like, yeah, those are kind of similar to each other. That's what this is representing. So basically based on user ratings and saying, oh, how close are users rated versus how close are movies rated, you can basically create this structure and figure out, you know, other things that are close together. So he's just doing this visualization just to kind of show these parts. But like, for example, he shows off like documentaries right here. You can see they're kind of like clustered and then they kind of spread out. You know, for example, this documentary probably is very different from the rest of these over here, but they're still documentaries. And then you can see here, it looks like he does comedy, drama, and romance, which I can zoom this in a little bit. Oh, I didn't like that. Okay, so you can kind of see this is probably not the best like coloring system because it starts looking brown, but you can kind of see like green is in drama. So you can see dramas are over here versus it looks like romance is kind of over here, but then kind of scattered around. So you can kind of see there's a little bit of romance, but it's not as clear as like as a drama. And then comedies were off to the left, which kind of makes sense. You would expect drama movies to be pretty far away from comedy movies, right? And you might see like romance, like, well, you could have romantic comedy, but you could also have something like a dramatic, you know, like movie that's about romance. So you can start picture like, I mean, what's really cool is that we never told the system this, and we'll talk about like a little bit how this is created. But with embeddings, we never actually described how to get to this point. Essentially, based on the user's input and the movie ratings, essentially, and seeing what users are similar to each other, you can actually create something that does a pretty good job of describing these parts. And you might find patterns that you might not have ever realized. So one thing I really like about this lesson, he has some exploring. He does things like, if you guys remember doing things like analogies, with like, you know, this movie is to this. Let me see if I can find it real quick. Yeah, I think he's, oh, there's like, he does like addition analogy solving, right? This is, I think it's kind of old school. I don't know if they actually do this anymore in the SAT, but like shower is to deluge versus as something is to stare. And so he does things like brave is to cars to as Pocahontas is to something. And so you can kind of like do these parts, and he does things like you can add movies together. So for example, I think he shows like Scream, and I'm trying to think of a good example here that he had. Oh, Scream and Psycho. It's like, what's the movie that is like, what plus Psycho would equal Scream? And I think he ends up getting like some kind of comedy movie. Oh, he gets like Scream 3, but also Piranha, Freddy. Oh, these are similar. I'm trying to think, what, does he actually say what actually happens here? But basically he realized like, oh, you can think of Psycho as being like a scary movie, right? But then Scream is kind of like a scary but slash funny movie, right? So this is basically the part that's missing here is the funniness. And so you can actually find other movies that are kind of similar where it's like, oh, well, obviously Scream 3, Scream 2, but Piranha, it's like, well, it's supposed to be scary, but also there's probably people who enjoy it as like kind of like, you know, as a funny thing. So I think it's Freddy versus Jason. It's not a super serious movie. So there's some really cool stuff. So I would highly recommend doing that lesson right here for embeddings. Because one, I think it teaches you embeddings pretty well, specifically matrix factorization, and then also gives you an idea of like how recommendation systems would work. So definitely, I would say supplement that with learning. The learn itself will actually, this will actually use sklearn and a little bit of pandas. I think it's mostly sklearn. Yeah, there's just a little bit of pandas in here. But just know for the learn curriculum, it focuses on Spark, which I think is important because Spark really, PySpark, will allow you to do like distributed systems and everything like that. So just know it's like, this is probably going to be more familiar if you're familiar with pandas, which you probably are. This is more like a small little model. But if you were to basically extend this out, the same concepts, but extend this out, you'd extend it out probably something with PySpark, something that could use a distributed system. So yeah. Anyway, so that's all I had to talk about for recommendation systems. Do you guys have any questions? Anything you'd like to ask? All right, cool.